This video is about exoplanets. Exoplanets, or sometimes known as extrasolar planets, are planets that orbit other stars. There are many different types of exoplanets, and many of those types are of planets we cannot find in our own solar system. First, there are large planets. Now, there are a few different types of these. First, the first type of large planet, and in fact one of the first type of exoplanets that we discovered, are hot Jupiters. Hot Jupiters are a type of large gas giant planet that orbit very close to a sun-like star. The first hot Jupiter that we ever discovered was called 51 Pegasi b, orbiting the star 51 Pegasi. These planets are so close to their stars that their orbits take just days. They take less than a week. Now, it should be noted that these planets also often orbit stars that are about the same size as the Sun, or the same size as the Sun, which means that they are extremely hot, among the hottest planets that we know of. These planets are also tidally locked, meaning they rotate as quickly as they orbit their star. This means that they always show one face to the star, just like how the moon shows only one face to us at all times. The moon is also tidally locked. Of course, there are also regular gas giant planets. Now, one interesting thing is that the data from the Kepler Space Telescope has actually shown 121 gas giant planets in the habitable zones of various stars, the habitable zone being the area of the star's orbit where temperatures are moderate enough for liquid water to exist. Now a gas giant planet by itself would not be suitable for life, as a habitable zone would normally allow. However, gas giants are known to have, especially gas giants that are not hot Jupiters, are known to have systems of moons. The two gas giants in our solar system have dozens of moons. These moons, if they are large enough, could have atmospheres, and if they're in the habitable zone, they could have liquid water on their surface, which would then allow for life. Now, this is a Chthonian planet. Chthonian planets are related to large planets, gas giants, mainly to hot Jupiters, and it's simply when a hot Jupiter has its atmosphere blown off by the extreme heat and radiation that it faces. This eventually blows away most of the planet and leaves only the rocky core. Now, a Chthonian planet would also have these. A Chthonian planet would also be tidally locked, just like a hot Jupiter, and they would orbit at about the same distance as a hot Jupiter, since it is basically a former hot Jupiter. Now, for ice giants, there's not much to say about these. These are simply planets like Uranus and Neptune. They are much larger than the Earth, but they're not large enough to be gas giants. They do generally orbit further out, and we don't see as many of these orbiting extremely close to their star like hot Jupiters do. Now, Trojan planets are basically moons. These are planets that orbit other planets. We have not actually found any of these yet, but we do believe they exist, and we have reason to believe they do exist. The problem is that, for example, imagine we're in another solar system and we're looking at our solar system. How easy do you think it would be to find the moons of Jupiter or Saturn? It would be very difficult. And this is actually where it ties into gas giants, because these orbit large gas giants, and if that gas giant is in the habitable zone, a large enough Trojan planet could, as I said before, have an atmosphere and water. Now these planets, they would be shielded by solar radiation by a gas giant's magnetic field, but they would also still face a lot of radiation from the gas giant itself. So it is still doubtful if a Trojan planet could support life even if it did have an atmosphere and liquid water, simply thanks to the radiation from the gas giant. Another potential problem is that planets that orbit gas giants face tidal forces from gravity. These are similar to the forces that cause Earth's tides as the moon orbits the Earth. These forces around a gas giant could be much more extreme, and if this planet has plate tectonics as well, just like on Earth, then this could possibly cause the planet to be extremely geologically active. This could be a problem, especially for larger Trojan planets, aka Trojan planets that would need to be large to support large atmospheres and water. Now, rocky planets. These are the types of planets that we are the most interested in right now. They're the ones that we are looking for the most. Now, we found many of these types of planets, and there are many different types of them. They're often classified on their size and also on their potential similarity to Earth. There's actually there's something called the Earth Similarity Index that says how close, how Earth-like a planet could be. Now, probably one of the more well-known rocky planets are super-Earths. These worlds are larger than our Earth, but they are not large enough to be an ice giant. These planets have actually previously been described as super habitable planets. Now, a super habitable planet is a theoretical type of planet that could actually be better for life than Earth. This is something that's hard for us to imagine because Earth is the only planet that we know right now that we are sure can support life. And it has also done a very good job of supporting us. So it's hard to imagine a planet that would be even better than Earth. However, this is possible. For example, take a planet that is twice the mass of Earth and slightly larger in its radius. This planet would have a much hotter core, and its gravity would also be higher. These two things combined could allow for the planet to trap more gases and have a thicker atmosphere, and have a stronger magnetic field which would make it easier to keep that atmosphere. The hot core would also allow for better or more active plate tectonics on Earth than on Earth, and what this would do is it would recycle all the rocks and minerals that life would use to keep itself going. And this type of world would be better because many of the barriers that exist on Earth, for example, things like extremely harsh deserts and perhaps even icy areas like glaciers, or not glaciers, but places like Antarctica that are basically covered in ice, would actually not exist here or would be heavily reduced in their size. In other words, this planet would be much more lush and green, at least in terms of possible plant life, than Earth. There is also the possibility that these planets could actually have smaller or lower ocean basins, or it would decrease ocean basins, which, well, in other words, could actually possibly make oceans, or at least some parts of oceans, more shallow, which would help marine life, help with the formation of things like coral reefs. Now, after super habitable planets and super Earths, there are just regular old habitable planets. These are simply planets that orbit in the habitable zone of a star and would have atmospheres with liquid water on the surface. These don't need to be super Earths. There are planets that are the size of Earth, or perhaps even smaller than Earth, that orbit in habitable zones of stars. they would not be quite as amazing or exotic as super habitable planets, but they would still be decent for life. Now, this is where star types come in. There are different types of stars, and different types put out different amounts of light and heat and overall energy, and also, more importantly, have different lifespans. For example, a large blue star will live for millions of years. A mid-sized yellow star like our sun will live for billions of years. A small red dwarf star, or red stars, would live for hundreds of billions of years, perhaps over 1 trillion. Now, this is important because small red stars are some of the stars that we found a lot of rocky planets in the habitable zone. And one problem with these stars, especially with the very small stars, the smallest type of red dwarf stars, is that they flare up much more than the sun does, and the flares they put out are extremely powerful. These solar flares, if a planet does not have a proper magnetic field, could easily strip away the atmosphere. However, we have found there is actually another problem that these planets would face, and this is the aforementioned issue of tidal locking. Now, these stars, although they are much smaller than the sun, and as such would have less gravity, in their sense are less massive, their habitable zone is also much closer in than with the sun. For example, with the now famous system of TRAPPIST-1, all planets in that system orbit closer to their stars than Mercury does to the sun. Now, this means that all of these planets will be tidally locked. And this creates a bizarre type of world called an eyeball Earth. This is an unofficial term. It's not used very much scientifically, but it's a good way to describe these, because these planets would have layers on different hemispheres. For example, a planet like this, since it's tidally locked, would only show one side to its star, and this would mean that one side receives much more light and energy than the other side. Now, if an eyeball Earth does not have a large atmosphere and good magnetic field, this would mean that the side facing that star would be completely dry and too hot to have liquid water, and the side facing away would be covered in ice. There would be a small band of habitability in where those two hemispheres meet, but aside from that, this planet would be very hostile. However, a planet with a thick atmosphere, or at least an atmosphere similar to Earth's, would be able to moderate those temperatures enough to allow more and more liquid water to start forming. Now, large oceans do have a similar effect on temperature as an atmosphere, which would moderate the temperature even further and allow for the temperature on the hot side to be heavily reduced, and would circulate much of that heat over to the cold side. However, this does still have a problem. Since these planets would only have one side to their star, this means that the dark side would never receive any light, which would make plant photosynthesis impossible. This means that complex life may not develop on the dark side. Now, there are forms of bacteria that can live using chemical reactions in the soil to produce energy, but it is doubtful if these forms of life could evolve to form complex environments. However, this does still mean that half the planet would be usable to complex life that we know. Now, there's also a potential type of rocky planet called a carbon planet. Now, in order to know these planets, we first need to know what is the difference between carbon and silicon in regards to planet formation. Now, most of the dirt and rocks on Earth are made from silicon. It's simply the element that makes up most of our surface. And while carbon and silicon are both quite common here, but the ground on Earth is made mostly of silicon, while life is made of carbon. Our bodies, plants, animals, we're all different forms of carbon. And a carbon planet, it doesn't necessarily need to have life on it, but it's simply a planet where what makes up the ground, what makes up the surface is reversed. Instead of being made mostly of silicon, it would be made mostly of carbon. This planet would be similar to Earth in some ways, and in some ways that for this world's basic makeup would be similar to Earth, in which they would have geological features and possibly oceans of liquids, but what those features are made of would be different. For example, a carbon planet, even if it is in the habitable zone of its star, would not have any liquid water on it, because that water would react with the elements in that planet and would turn into things like carbon monoxide. The atmosphere would be made of things like carbon dioxide and other such gases. There would be large deposits of hydrocarbon liquids. So these liquids would be similar to things like methane or oil. Imagine a river of diesel. There you have one feature on a carbon planet. Now, it is possible that these planets could still have things like plate tectonics, and the concept of silicon life is doubtful. It has been proposed because silicon is a reactive element. It can react with things and potentially form at least primitive life. But we do still think that carbon is superior to it. So a carbon planet would most likely not have very complex life on it, even if it does have life. But the possibility of a polar opposite Earth, where the ground is made of carbon and the life is made of silicon, is fascinating. Now, ocean planets are simply super Earth planets that we discussed before that are covered completely in water. These planets they would look maybe somewhat similar from a distance, since we would see water and clouds, but they would actually be very hostile. The oceans on an ocean planet would be far deeper than the ones on Earth. They are so deep that the bottom of that ocean actually wouldn't have any rock on it. When we go to the deepest oceans on Earth, we still find at the bottom rock. On an ocean planet, however, at the bottom, what would technically be, in geologic terms, the floor of that ocean, there would simply be a place where the pressure of the water is so high and so extreme that the water is crushed into a solid, similar to how the interior of gas giants is like. Once you go deep enough into a gas giant like Jupiter, you get to a point where gases are compressed into a liquid, and then eventually those liquids, as you go deeper, are compressed into solids. A similar thing plays out on an ocean planet. This type of ice is called Ice 7. It's formed when water is heavily compressed at moderate temperatures. So in order for this to happen, the temperature would need to be at about room temperature, which is possible on an ocean planet. It is possible also that life could form on one of these planets, but it would not be very complex because it would probably not be very complex because there would be nothing for it to actually attach onto, and plus there is no rocky bottom. So, for example, if something were to float down there, first it would probably not survive the pressures. Though the pressure needed to compress water that heavily is extreme, and even on Earth, the pressures at the bottoms of oceans are far too high for most life forms that we know to survive. So life, if it does exist on an ocean planet, probably wouldn't be very complex life. Free-floating planets. Now, free-floating planets are actually potentially the most common type of planet in the galaxy. There might be more free-floating planets, in fact, than there are stars in the galaxy. These are also known as rogue planets. They're simply planets that don't have a star to orbit. They float across the galaxy. Now, these planets were most likely formed in a solar system when that solar system was young and ejected out. The beginning phase or the beginning era of a solar system is often very chaotic. There are collisions happening everywhere, things are still forming, planets are finding stable orbits, and this can result in things being suddenly affected. For example, there was actually a time in Earth's ancient history, billions of years ago, when a planet the size of Mars collided with Earth. And this collision helped create the Moon when it ejected large amounts of debris around Earth. If something like this, or some other process, could possibly eject a planet out of a solar system entirely, and that planet would simply be left to wander through space. A free-floating planet would still have some heat on the inside thanks to their cores, but the outside of for example, a rocky free-floating planet would be completely frozen. However, it is possible that a gas giant rogue planet would still have a system of moons around it, and this system would be heated up by the tidal forces from the gas giant's gravity, and similar to what happens in our solar system with moons like Europa, this heating would allow for below the planet's outer shell for there to be liquid water, and with that you have possibly life. This is actually very similar to what happens on Europa. Without the life part, we're not completely sure if life exists on Europa yet. But Europa in our solar system, this moon of Jupiter, is very far from the sun. The outer shell is frozen, or at least it's supposed to be frozen, but thanks to the constant pulling from Jupiter, this does two things. One, it constantly cracks Europa's outer shell, which is why we can see all those fissures with our probes, and this also heats up the moon's interior, which is why it actually has a vast ocean under that surface. This could happen with a free-floating gas giant as well. This is possibly the most bizarre type of planet, and it's actually the very first exoplanet that we ever discovered. A pulsar is a type of neutron star, which is a type of stellar remnant, the remains of a very large star, in this case a large blue star, a blue giant star that ended its life and exploded. When no planet that orbits a blue giant star would survive a supernova, but after that event takes place, some of that debris can actually come back and form planets. These planets would most likely not be habitable, as they're constantly washed over by ionizing radiation from the pulsar, which would break down the molecules and DNA needed to form life. Now, but these planets, they can actually be of many different sizes. We have seen planets smaller than Earth, we have seen super Earths, and even gas giants orbiting it. There is a possibility that, if for example, with a planet with a very thick atmosphere and a strong magnetic field, the surface of the planet would be shielded from most of the radiation, but then we have a whole new set of problems that life would need to endure. We have actually found planets in the habitable zone of a pulsar, but again, the chance of life existing on those planets is very low. Thank you. I hope you learned a few things about exoplanets here, and I'll see you soon for another video. Please subscribe.